hi everyone. I'm sorry, this is going to be backwards. I can't flip it here with my technology that we have. But I wanted to record this for you as we go through history of the atomic model. Since I'm not able to be there with you today, I apologize for that. And I can't wait to see you tomorrow, hopefully. So we talked about the first model being Democritus and John Dalton's model of the atom, which was indivisible. Atoms are not able to be broken down into smaller parts. They make up everything. They're able to be combined to form new substances. So Dalton was sort of right, but he missed the indivisible part. Our second model we attribute to J.J. Thomson because he theorized and discovered that there were little things in there called the electron. And he gave us the concept of there being something in the atom that makes it negatively charged, using Ben Franklin's term negative. And J.J. Thomson names those with the awesome rad name electron. So that's our electron model in 1904. Then we talked about the oil drop experiment here with Mr. Millikan, the American physicist guy with a nice bow tie. And we'll go over some more of this in class, but he gives us the actual mass of the electron and the charge of the electron. And again, this is backwards. You can follow along on your presentation if you'd like. He wins the Nobel Prize in 23 for his discovery of the charge of a single electron and the mass of the electron, which is 1/2000th the mass of a hydrogen atom, or the proton in a hydrogen atom. And what that helps us realize is that the electron is very tiny, 1/2000th is the mass of a proton, but it has the same charge as a proton. So even though the electron is super tiny, it has the same charge, and that's pretty cool. So then we get our next model, which is going to have to do with the nucleus, and this guy, Mr. Ernest Rutherford. We'll talk about de Broglie and Henry Becquerel, I can never say his name correctly, Henri Becquerel, 1852 to 1908, helps us figure out basically radioactivity, which is going to be a whole unit of study that we get into in the spring, talking about neutron dissipation and radioactivity. But he wins the Nobel Prize in 1903, which is the year of Einstein's Annus Mirabilis, or miracle year. So I'm not saying Einstein should have won the Nobel Prize that year, but it takes a few years for us to give him that award. And then we have Ernest Rutherford. He was an English or a British scientist, and he gives us the gold foil experiment. He and his assistants, he wasn't the only one working on this. Rutherford lives until 1937, and is an incredibly important scientist, and basically uses radioactive alpha particles shot through gold foil. We haven't talked about radioactivity yet, but the gold foil experiment takes radioactive particles that are called alpha particles, and we'll talk about these, and he shoots them through a little piece of gold foil, like tin foil, but made out of gold. And that's important because gold typically doesn't interact with electrical situations in certain mediums. But in some mediums, gold is a very, very, very good conductor of electricity. So it depends on temperature, pressure, and all sorts of things. But if you use any high-end audio equipment, like monster cables even, overpriced, but high-end audio equipment a lot of time will use gold as the conductor instead of something like copper, because it can be a very good conductor of electricity and energy and information. So Ernest Rutherford realizes that most particles pass through the gold that they're shooting at this foil, and some were deflected. Now, here's an image of the gold foil experiment. We have a radioactive substance, we have a beam of alpha particles being shot out, and then we have the screen that's collecting the particles that get shot out. And what Rutherford realizes is that there's something inside of the atom that has mass that's not the electron. So if Thomson was correct and the little electrons were just kind of scattered in, the gold foil experiment would have gone differently. So Rutherford says there has to be something in the middle of the atom, in the nucleus of the atom there, in the center. I'm trying to, there we go. And that explains why some of these alpha particles were bouncing off of the gold foil in certain areas, which if Thomson were correct, it wouldn't have been the case. So the conclusion is that the atom is mostly empty space. That's true. His second conclusion is that the atom has a very dense positive positively charged center, which is also great. And he names it the nucleus. So Mr. Ernest Rutherford, using the gold foil experiment, here's Mr. Rutherford at work, doesn't have a bow tie on, he gives us the name the nucleus. We don't know about the protons yet, but he understands that there's a small positively charged center of the atom. So that gives us kind of what we associate with atomic theory. Like you'll see this drawing, the Rutherford model a whole lot, this in the Bohr model. So the Rutherford model, the atom with the very tiny positively charged dense center that Rutherford calls the nucleus. Mostly empty space. So we've got the nucleus and the electrons orbiting the nucleus here. We're getting there. So this is early 1900s. Very influential. We're going to watch this video when I get back, so you can watch it.
This is Cambridge University in England, where...
Okay, thank you. We're going to watch that when we get back. It's a good video. But there's a problem with Bohr's model. What keeps the electrons from crashing into the nucleus as they lose energy? So we have this guy named Niels Bohr, and his name's kind of a pun because evidently he was a very boring speaker. He's Danish, so they have great names in Denmark. My family's from Denmark, so you're also Niels Bohr, very, very, very influential physicist of the 20th century. And he realizes, just a few years after Rutherford's model gets published, that it's on the right path and there's something there. But what keeps the electrons from crashing into the nucleus? Like, why do the electrons stay where they are? So he's going to set out to try to figure that out. And he solves the puzzle by adding to Rutherford's model an idea of fixed orbits, which we sort of still use today. So in 1913, Bohr proposes a model where electrons traveled around the nucleus in what are called fixed orbits. It's called the planetary model, or the orbital model, if you will. And the electrons jump orbits when they gain or lose energy. So if you electrically charge up something and you add electrons, and you get the electrons really excited, the electrons can actually jump in their orbits around the nucleus. Again, we don't know about protons yet, but we know the nucleus is there and it's positive. So in Bohr's model, the fourth model, so we had Dalton, then we had Thomson, then we had Rutherford, and just a few years later, we have Bohr's model, the planetary model, the orbital model, the Bohr model, the Danish model you'll hear it referred to as. Bohr leads a group called the Copenhagen Group, which is very influential in particle physics. Back in the day, they're all passed away now. But you see these electrons are in orbit. So this is the fourth model of the atom, the Bohr model. And finally, in 1913, we get this guy, Henry Moseley. Very sad story about Mr. Moseley. He was drafted into World War I. Well, no, he actually went to serve in World War I. And he was a fighter pilot, and he was shot down at a pretty early age. So we always wonder what else we could have known, because people like Einstein considered Moseley one of the most brilliant scientists of the early 20th century. So Mr. Moseley, taken away from us because of World War I. But he names the individually charged particle in the center of the atom the proton. We don't know about neutrons yet. And he establishes experimentally, remember I said there's a difference between theoretical physics and experimental physics. Moseley was an experimentalist. That the atomic number of the atom defines the identity of the element, or the number of protons, which is true. That's why we have that periodic table over there. So the number of protons determines the type of atom. So Henry Moseley, brilliant guy, taken from us way too soon. Rest in peace. Moseley was killed at the age of 27 after giving us the proton and the concept of atomic number defining the atom. 1932, only 1932, like my grandparents were alive in 1932. James Chadwick looks like a American professor around that time, doesn't he? No bow tie. He died, he dies in 1974, shortly before I was born. But in 1932, James Chadwick helps us figure out what the neutron is, and we'll talk about how we get to that, or how we got to that, how we got there. So we have our last model is the Bohr model, that orbital model. That's not the current model of the atom. We're going to get to that tomorrow. But leading up to the atom, we have some friends over here. Here's Mr. Einstein, and over here is a guy named Max Planck. The Planck, I think, is very important. In 1900, Planck proposed a relationship between a quantum, or a bit of energy, and the frequency of radiation. So we'll talk about, again, when we get to radiation, what that means. But just know Max Planck is very influential in giving us the current model of the atom, as is this guy, Mr. Einstein, who basically proves that atoms exist, Brownian motion, as we call it. introduced the idea that electromagnetic radiation, which is what we're leading back up to, this is light, electromagnetic radiation, waves, has a dual wave particle nature. So light moves as both particles and as a wave. And Einstein finally solves the answer that Mr. Newton was working on. Einstein called the particles that carry a quantum of energy photons. So photons. Mr. Einstein flips up that term, or he gives it that name. Photons is what we call light, so this thing is being projected using photons. But photons just mean any kind of quantum of energy. Sounds like a James Bond movie title. It's a quantum of energy that is traveling on a wave, a photon. So it could be light, but it could be any number of things as well. Then we have a couple more folks. Louis Borloo, Werner Heisenberg down here. If you watch Breaking Bad, you might have heard the name of Heisenberg, taken from Werner Heisenberg here. Electrons considered waves confined to the space around the atomic nucleus. We'll talk about what that means, but basically electrons are waves. That's true. And then we have Heisenberg, and we're going to go over all this in person. I just wanted to introduce it to you while I'm not there today. One of the key pioneers of quantum mechanics. He develops the Heisenberg uncertainty principle, which we're going to spend some time talking about. And basically says it's we're unable, it's impossible, there's a bell, to determine both the position and the velocity of an electron. We'll talk about why that's mind-bending. And we get quantum theory, thanks to this guy, Erwin Schrödinger. We say Edwin. Dual wave particle nature. He gives us an equation called the Schrödinger equation. And that's the Schrödinger equation. This is our wave function. This determines everything, including you and me and all the things that we can see, to quote Monty Python. And the Schrödinger equation is incredibly, incredibly beautiful. And this is the most mathematically proven thing humans have ever done. We'll talk more about Schrödinger and his equation when I get back with you all tomorrow. After you look over your note sheet here, there is an assignment on Classroom. And I'll see you all very shortly.